Very good evening to everyone. So I welcome you all for the day 2, session 3 of 6 days online FDP titled Innovations in Additive Manufacturing for Green and Sustainable Future. The session 3 will be delivered by Dr. Cyril Joseph Daniel. I am very happy to introduce our resource person, Dr. Cyril Joseph Daniel. Dr. Cyril Joseph Daniel received BE Mechanical, ME Manufacturing, PhD Mechanical from Anna University. Currently, he is doing research on failure analysis of welding electrodes. He has done research on welding metallurgy, material testing, metallurgical characterization, solid state material processing, and additive manufacturing. He has published more than 20 indexed journals with the collaboration of IIT Madras professors. He is currently taking position as Senior Development Engineer, R&D Filler Metal Divisions, ESAP Corporation. Also, he is taking postdoctoral research fellow position in ESAP Industry Limited. Welcome you, sir.
Thank you, doctor. Shall we start the presentation?
Now I request our resource person to start session 3.
Thank you, doctor. Right now I'm in office, so just I turn off the camera and I will start the presentation. So, good evening, everyone. First of all, I would like to thank both the seminar coordinator, Dr. Rajashekara and Dr. Radhika Madam for giving me this opportunity to connect and share with you all today. Let me introduce myself. Myself, Dr. S. Cyril Joseph Daniel, and I currently working as a Senior Development Engineer in the Filler Metal Division at ESAP India Limited, Chennai. At ESAP, my work revolves around alloy development for diverse applications, and I am deeply involved in research and development of welding filler metals, including both flux and solid wires. My recent industry work mainly focuses on fusion-based welding processes, but my academic journey took me into very exciting direction. Specifically, I pursued my PhD in the field of solid-state additive manufacturing, with a special emphasis on nickel-based superalloy 718, tailored for high-temperature application. This is why the topic we are discussing today feels like a perfect fit for me. I will share my screen. Wait. Are you able to see my screen, Professor?
I think it is loading. Yes.
Okay. So during my research days, I got hands-on with the fundamentals of solid-state additive manufacturing. One of my main area of focus was studying the thermal stability of materials built additively, which led me to dive into techniques like infrared thermography to understand thermal effects during the solid-state process. It was fascinating to metallurgically characterize the material layer by layer and see how properties evolve. Beyond the material building process itself, I had a chance to evaluate real-world high-temperature applications, performing wear, creep, and hot corrosion studies on friction surface alloy 718, which experiences really broadened my perspective. Now I am in my current role at ESAP. I strive to bridge the gap between industrial requirements and academic research, advancing both filler metals and cutting-edge additive manufacturing technologies. My sincere aim is to share insights I have gained during my PhD, as well as bring in the industry's perspective on requirements, challenges, and future scope for solid-state additive manufacturing. So I look forward to taking you through these topics and having a great discussion. So let's get into the presentation. Today, I will be presenting on the topic of solid-state additive manufacturing. I will begin with the fundamentals and general overview of additive manufacturing, providing a foundation on how this technology has evolved and its growing significance in modern manufacturing. Next, I will move on to a comparison of fusion-based additive manufacturing and solid-state additive manufacturing. In this section, I will highlight the key differences between these two approaches, emphasizing the limitation of fusion-based method and the unique advantages that make solid-state routes particularly important. Following that, I will provide a detailed discussion on the principle and working mechanism of different solid-state additive manufacturing techniques. Each method will be explained in terms of its operating principles, process characteristics, and its role in addressing the challenges of traditional fusion-based approaches. The presentation will then shift focus towards the material science aspects of solid-state additive manufacturing, especially looking into microstructural evolution during processing and how these microstructural features directly influence the mechanical properties of the additively built components. This part will explore grain refinement, phase transformation, defect mitigation, and their overall impact on the performance of the additively built material. So finally, I will discuss the application challenges and future trends of solid-state additive manufacturing. This will include its current industrial relevance and the technological barriers that need to be addressed, and the potential pathways for further development in both research and commercial domains. So I will be presenting the fundamentals of additive manufacturing, often referred to as additive manufacturing (AM) or 3D printing. Additive manufacturing is a transformative technology in the manufacturing world, enabling the creation of three-dimensional objects by building them layer by layer from a digital model. To begin, traditional manufacturing methods like machining or casting often involve removing material or shaping
Yes, sir.
material in molds. In contrast, additive manufacturing is fundamentally different because it adds material only where needed, layer upon layer, constructing a final part directly from the digital design. This process greatly reduces material waste and allows for the creation of complex geometries that are difficult or impossible with conventional process. The process starts with designing a part using computer-aided design CAD, which creates a precise 3D model of the object.
I
This
think
model is then converted
slide
into
is not
digital.
moving.
Sorry.
Still, we are in the slide one. It is. I think it is not moving, sir.
Okay. Wait, I will check.
What about others? Can you see the? I
Slides are
think still it
visible.
is. It is visible, but it is
Slide-
not moving.
Yeah, it's not moving.
Okay. Wait,
Yes,
wait.
So
yes.
yeah, it's
Can
okay
you
now.
change it into full screen mode, sir? Yes.
Yes.
Slideshow, sir, slideshow. Yeah.
Now is it okay?
Yeah, sir, it's okay, but make
But
it
it is not
slideshow,
in
sir.
the full screen mode.
Full screen.
Showing in full screen for me, but
Sir, make it slideshow.
yeah, it is in slide mode only. Wait, wait, wait. Professor, is it okay now?
No, sir.
I am in slide number 3, fundamentals and overview. It is
Yes,
in
yes. We can see
slideshow
this
now.
third slide, fundamentals
Okay.
and overview. But if it is a full screen mode, it will be very useful for the better view.
It is in slide view mode only, Professor. I don't know why. Okay. Professor, shall I proceed? Is it okay? Is it visible to you all?
Can you press F5? Shift F5.
Okay.
Shift F5.
Yeah. I pressed Shift F5, but nothing happened. Okay. It is in slide view mode.
It is.
Are you
It will
able
be
to
under
see?
view option. It will be under view option.
Wait. Give me a minute. Sorry.
Yes, now it is okay, sir.
Professor, am I audible?
Yes, yes, yes.
Okay. Okay, sorry. So, how did it stop? Okay. So the additive manufacturing process starts with designing a part using computer-aided design, which is CAD software, which creates a precise 3D model of the object. This model is then converted into digital file format suitable for printing, such as an STL file format. The printer software slices this model into thin horizontal layers, and the additive machine follows these layers instruction to build up the object from the bottom up. There are several popular additive manufacturing technologies. One common method is fused deposition modeling, or FDM, where a thermoplastic filament is melted and extruded layer by layer to create a part. Another widely used method is powder bed fusion, which uses a laser or electron beam as a source to selectively melt and fuse the powder metal or plastic into dense pot. Other technologies include material jetting, which deposit droplets of material, and VAT polymerization, which cures liquid resin layer by layer using light. Material used in additive manufacturing range widely from plastic like PLA and ABS to metals such as titanium, stainless steel, and aluminum, and even ceramics and composite in specialized applications. One of the major advantages of AM is its ability to produce high complex and customized parts without the need for dedicated tooling or molds, making it ideal for prototyping and small batch manufacturing. It also enables rapid iteration during product development, reducing time and cost significantly. Additionally, the layer-by-layer nature of process leads to less material waste compared to subtractive method, that is conventional manufacturing methods. However, there are challenges to consider. Surface finishes from AM parts can require post-processing to meet quality standards. Mechanical properties may vary depending on the process and materials. And production speed and cost can be limiting factors for large-scale manufacturing. Today, additive manufacturing has found a significant application in aerospace where lightweight and complex parts are needed. In healthcare, for custom implant and prosthetic in the area they used, and in automotive and consumer products for rapid prototyping and customization. AM is expected to evolve with faster machine, multi-material capabilities, integration with smart manufacturing and Industry 4.0, and advances in material and printing techniques. In summary, additive manufacturing is not just a new way to make things, but a fundamental shift in manufacturing philosophy, moving from subtracting material to adding material, which opening new possibilities for product design and manufacturing workflows. So let's start with the simple question. What are the different additive manufacturing process? So the additive manufacturing classified into two different categories based upon the roots. First one is fusion-based additive manufacturing, and another one is solid-state additive manufacturing. Each of these categories has its own way of building parts, its own advantages, and of course some challenges. In fusion-based processes, which are probably the more familiar one, here the raw material, usually in the form of metal powders or wires, is completely melted using high energy source such as laser or electron beam, and then allowed to solidify layer by layer. Processes you might have heard of include powder bed fusion, selective laser melting, electron beam melting, and direct energy deposition. The biggest strength of fusion additive manufacturing is its ability to make very intricate and complex geometries, parts that would be almost impossible to produce using conventional methods. That's why industries like aerospace and healthcare love fusion-based additive manufacturing. For example, in aerospace, turbine blades with internal cooling channels can be built using powder bed fusion. In healthcare, pattern-specific implants such as custom hip replacements are possible. Even high-performance automotive companies like Bugatti, for instance, have used it to make titanium brake calipers that are both lighter and stronger than conventionally manufactured parts. But there is a flip side. Since fusion involves melting and resolidification, we also inherit some casting-like problems such as porosity, etc. Issues such those kind of defects like porosity cracking, residual stresses, and distortion can occur. And the microstructure often shows columnar grain, which makes properties very different from traditional manufacturing and solid-state additive manufacturing. Anisotropic, meaning the part behaves differently depending on the direction of loading. So now let's contrast that with solid state additive manufacturing. This category is completely different because we don't melt the material at all. Instead, we rely on plastic deformation, friction, ultrasonic energy, or high velocity impact to bond the material together at even at temperatures, low temperatures, well below the melting point. Key processes here include friction stir additive manufacturing, additive friction stir deposition, ultrasonic additive manufacturing, and cold spray additive manufacturing. The biggest advantage of solid state additive manufacturing is here there is no melting, as I said earlier. We avoid solidification related effects entirely. So no hard cracking, less porosity, and lower residual stresses. The microstructure usually comes out finer, equiacid, and isotropic, giving us better mechanical properties overall. Solid state methods also open the door to using materials that are usually unfriendly to fusion, like non-weldable alloys that would otherwise crack if we try to melt them. For example, in aerospace, friction stir additive manufacturing has been used to join large aluminum panels and structural components with exceptional strength and integrity. Cold spray is another fascinating technique. It blasts metal powders at very high speed to build or repair surfaces. This is widely used to repair turbine blades, apply protective coating to industrial parts, and even build large near net shield structures at relatively low cost. Importantly, these processes don't require expensive vacuum or inert gas chambers, so they are often more scalable and affordable for large builds. This is one of the important things in solid state additive manufacturing. So, so now let me explain the difference between fusion additive manufacturing and solid state additive manufacturing in a structured way. I made a quick comparison. First, looking at the basic process, fusion-based methods work by melting the feed material, which then solidifies to form the layers. In contrast, solid-state methods work below the melting point and rely on plastic deformation and bonding to join the material together. Coming to examples of processes, in fusion additive manufacturing, we have powder bed fusion, selective laser melting, electron beam melting, and direct energy deposition. On solid state additive side, the common ones are friction stir additive manufacturing and friction stir deposition, ultrasonic additive manufacturing, and cold spray techniques. When we compare the temperature ranges between two processes, fusion processes have to run at or above the melting temperature, whereas solid state processes usually operates between 60 to 90% of melting point. That is 0.6 to 0.9% of melting temperature without actually causing melting. In terms of feedstock types, fusion additive manufacturing typically uses metal powders or wires, while solid state approaches rely more on solid rods, plates, and strips. Now, about environmental requirements, fusion processes usually need a controlled atmosphere such as vacuum or inert gas to avoid oxidation. But solid state additive manufacturing usually does not demand that kind of strict environmental control. If we talk about microstructure, fusion processes tend to produce columnar grains and can show solidification defects, whereas solid state processes are known for producing fine equiacid grains with much more isotropic microstructure. With respect to defects, fusion is more prone to porosity, hard cracking, and residual stresses, whereas solid state processes avoid porosity and hard cracking and also have inherently lower residual stresses. Coming to geometric capabilities, fusion is very attractive because it allows us to build highly complex shapes and geometries, but solid state methods are somewhat limited because the tool must physically access the build area and the feedstock form can restrict the geometry. In terms of material range, fusion is somewhat constrained to weldable alloys and sometimes only to alloys that can be automated into powders, whereas solid state additive manufacturing can handle a much wider variety of alloys such as titanium, nickel, copper, aluminum, stainless steel, mild steel, and so on, including non-weldable materials. If we compare mechanical properties, fusion produced parts tend to be anisotropic, which means their properties vary depending on directional, while solid state process give us more isotropic properties and often better overall mechanical performance. Now, regarding the equipment, fusion needs laser, electron beams, powder feeders, and control chambers, while solid state methods use tools like friction stir heads, ultrasonic horns, and cold space systems. Finally, when we consider production speed and build size, fusion methods are restricted by their heat input, cooling rates, and machine size, whereas some cases solid state process can be faster and allow larger build envelopes because they don't deal with the solidification constraints. In summary, fusion additive manufacturing is excellent for producing complex geometrics, but it struggles with heat-related issues because of melting and solidification, and it has limited material flexibility. Meanwhile, solid-state additive manufacturing give us the stronger, more consistent properties and broader material options, but at the cost of geometry limitation due to the tooling involved. These are the major solid-state additive manufacturing method explored by various researchers. The solid-state additive is categorized into three different categories: friction welding based, and friction deposition based, and friction stir welding based. These are further classified into subcategories: linear friction welding based additive manufacturing technique and rotary friction welding based additive manufacturing comes under friction welding based additive manufacturing techniques, and friction surfacing and friction deposition comes under friction deposition based additive manufacturing. In friction stir welding based additive manufacturing, there are three different subcategories: friction assisted seam welding, additive friction stir, and friction stir additive manufacturing. First, we will start with linear friction welding additive manufacturing technique. Linear friction welding, often abbreviated as LFW, it is a sophisticated solid-state additive joining process that has become particularly vital in industries like aerospace, automotive, and energy industries due to its ability to produce high-quality, structurally sound welds without melting the base material. Unlike traditional fusion welding, where the metal melts and solidifies, LFW works by moving one piece in a controlled linear reciprocating motion against a stationary component while applying the high axial compressive force. This relative motion generates significant frictional heat at the fairing surfaces, the surfaces to be joined, which softens the material at the interface without reaching its melting temperature. This localized heating allows the material to enter the plasticized state, enabling atomic level bonding and forming a weld with minimal distortion and residual stress. The linear friction welding process can be divided into four distinct phases that ensure a strong and defect-free joints. The first phase is the initial contact and friction stage, where the relative sliding motion causes microasperities roughness on the surface, and it increasing the real contact and starting initial heat generation. And the second phase, called transition and conditioning stage, is where the one surface layers and oxides are expelled and a fresh plasticized layer forms at the interface due to frictional heating. This stage is crucial as it promotes clean metal to metal contact, which is improving weld integrity. Next comes to the third phase, known as the burn-off or equilibrium phase. Here, the axial forces increase, causing plastic flow of the softened material, which is extruded outward as flash. This results in a reduction, softening of the axial length of the weld assembly, and it ensures thorough the bonding across interface. The final phase is the forge or consolidation stage, where the oscillating motion ceases and the parts are held together under sustained pressure to cool and solidify the bond. During this stage, residual stresses develop as the material consolidates, but the solid state process helps keep these stresses lower than what occurs in fusion welding. In an additive manufacturing context, LFW has been adapted to build complex components incrementally by repeating these four stages multiple times in a cycle fashion. Initially, two base parts were welded to form a substrate. Afterward, smaller parts are subsequently joined to expanding substrate, with flash being removed by precision machining such as CNC milling to maintain dimensional accuracy. This approach enables the fabrication of large complex geometries that would be difficult or expensive to achieve with conventional manufacturing or fusion welding processes. One of the major advantages of linear friction welding based additive manufacturing is its ability to join dissimilar materials, including titanium, nickel based superalloys, steel, and even aluminum alloys. This capability opens design possibilities such as bimetallic components or using expensive materials only where mechanical performance is critical, making it cost effective. Furthermore, LFW produces near forged quality joints with excellent mechanical properties and minimal heat affected zones, which enhances the fatigue life and reliability of critical components. However, the process requires sophisticated machine control systems, rigid equipment which capable of handling high axial loads and precise oscillations, and involves additional cost due to machining of flash after each weld deposition. Despite these challenges, LFW is widely used by leading aerospace and automotive manufacturers like Boeing and Rolls-Royce to fabricate essential components such as aero engine blades, compressor discs, and structural automotive parts. When it comes to rotary friction welding, which is RFW, it is a really interesting technique. First shown as an additive manufacturing method by the Welding Institute in 2007. It is a solid state process, as we know, which means the material don't melt. Instead, one part spins while the other stays still in the spindle. And they are pressed together so that the friction between two material creates heat at the interface. This heat softens the surface and which, with enough pressure, they bond metallurgically without actually melting. The RFW process has two stages. First one is friction creates heat and the material is upset or deformed slightly. Then forging phase finishes the weld. This is the simple process of making additive joints. There are two types of rotary friction welding additive manufacturing. One where the rotation keeps going continuously, and another where a flywheel provides rotational energy. This idea to add parts layer by layer, making bigger components efficiently by just joining smaller pieces one after another. Things like the spinning speed, how hard the parts are pressed together, and how long they stay in contact all influence how strong the weld is and how the microstructure looks. For example, there was an application where stainless steel layers were joined to build a thick cylindrical component. The bond between layers was excellent. The weld zone showed finer because of the dynamic recrystallization during solid state additive manufacturing, which actually improves the strength compared to the original metal. But a couple of things to keep in mind that are this method mostly works for cylindrical shapes and create different zones in the weld area that can lead to varying properties within the component. Also, the welded layer edges sometimes create excess material called a flash, which requires finishing afterwards. In industry, you will find RFW used for joining similar and different shafts, attaching drill bit shanks, connecting valves, welding pipe flanks and gears together inside the gearbox. Overall, rotary friction welding is a solid, reliable technique that is growing in use for building strong, high-quality components layer by layer. When it comes to friction deposition additive manufacturing, it involves using two rods. One is a consumable rotating rod, and another is a stationary substrate rod. Both rods are attached to machine spindles and aligned along with same axis. The consumable rod is rotated and pressed against the stationary rod with a certain axial force. When these two rods come into contact, friction generates heat at their interface, which softens and plastically deform the material at the contacting surface. As this process continues, the amount of plastic material increases at the interface. Once the desired thickness of deposited layer is reached, the rod are withdrawn. Importantly, when the rotating consumable rod is stopped and pulled away, the plastically deformed material remains attached to the stationary substrate. This happens because the torsional shear stress at the interface causes the plasticized material to detach from the rotating rod and stay bonded on the substrate. For building multiple layers, after depositing a layer, CNC machining is used to flatten and prepare the surface before adding the next layer. This step is necessary to ensure good bonding and surface finish for subsequent layer. The whole process is influenced by several important parameters, including rotation speed of consumable rod, the axial force applied, and diameter of the consumable rod. The rotation speed is particularly crucial because it controls how much frictional heat is generated. Higher speed means more heat and better bonding quality. The axial force controls how well the deposited material consolidates. Increasing the force improves the adhesion, but tends to reduce the layer thickness and increases the formation of flash, which can lower the efficiency of the deposition. A larger consumable rod diameter allows wider deposit but requires more powerful machinery. An interesting aspect of this process is that the deposition occurs at the solid state temperature, which are above the material's recrystallization temperature, but well below its melting point. At these temperatures, the deposited material undergoes dynamic recrystallization, resulting in a fine microstructure, which generally improves mechanical properties compared to the parent material or properties which we have obtained from the fusion-based or rod or casting way. However, a limitation of friction deposition is that each layer has to be machined before adding the next, which raises production cost due to additional CNC machining. Friction surfacing is one of the most successful friction-based additive manufacturing techniques, and that is because of several great reasons. First, it offers a wide range of material selection, making it very versatile. It's pretty easy to operate compared to some other advanced methods, and it lets you build complex shapes and coatings layer by layer. Plus, it tends to give better mechanical properties like corrosion and wear resistance than many traditional coating methods. And it generates much less material waste, which is a big win for cost and sustainability. Uh, we start with something called mectrode, which is a rotating consumable rod that presses against the surface you want to coat. As it spins and presses down, friction generates heat right at the interface, which softening the tip of the rod without melting it. Once the tip gets soft and plasticized, you move the substrate. That is that's the surface to be coated in a steady direction. The softened material from the rod gets deposited continuously on the substrate surface, building up a coating layer. This is the process of friction surfacing additive manufacturing. You can add multiple layers this way. After you deposit a layer, you can use CNC machining to shape it how you want, then add another layer and keep repeating until you get the coating or part thickness you needed. If you're working on large surface, you might need a deposit material in multiple overlapping tracks to cover the entire area, and again machine the layers between passes. Several factors control how good your coating is. The rotation speed of the mectrode controls how much heat is generated, which plays a big role in how well the coating bonds. Moving the substrate slower causes a thicker layer, but means the material stays hot longer. Increasing pressure, pushing the rod down improves the bonding, but also makes the coating thinner and wider. The size of the metro mostly controls the coating width, but needs stronger machines for bigger rods. And in multi-track coatings, positioning the rod properly is key to avoid defects where tracks overlaps. Like any technique, friction surfacing has its own challenges. Every layer usually needs machining to get exact shape, which add time and cost. There is also a revolving flash extra material at the tip that reduces the efficiency. Complex part geometries with overhangs or downward facing surfaces are harder to coat well. Overall, friction surfacing is a powerful solid state additive manufacturing method. It offers excellent control over coating thickness and properties, uses less material waste, and produces coating with fine microstructures that are highly resistant to corrosion and wear. Now let me talk about some techniques that are based on the principle of friction stir welding. These include assisted seam welding, additive friction stir, and friction stir additive manufacturing. Collectively, we call them friction stir additive manufacturing or FSCATs. In these methods, metals are joined in a solid state, layer by layer, as like we have seen in previous additive manufacturing techniques. Um, Deposition of layer, which means we can avoid unwanted phase transformation and defects that usually occurs in fusion-based processes. The parts produced by friction stir additive manufacturing techniques usually have fine microstructures, as we've seen in friction surface additive manufacturing. As we know, with grains that are almost equal in length, and this results in fewer defects overall. So essentially, friction stir additive manufacturing technique combines the strength benefits of friction stir welding with the flexibility of additive manufacturing. This makes it possible to manufacture even complicated shapes in relatively less time. Currently, this technique is mostly used in research for producing simple shape, but it clearly shows promise as a flexible and hybrid manufacturing technique for the future. The figure shows the different stages in the friction stir welding processes. We begin with first stage, the positioning stage. Here, the base metals that need to be welded are clamped on the FSW machine. Normally, these are placed on a backing plate, which helps in dissipating the heat generated during welding. Next is the plunging stage. At this point, the rotating tool is pressed down vertically at the start of the joint line. The tool goes down until its shoulder touches the surface of the base metal, and this marks the beginning of the deformation process. Then comes the dwelling stage. Once the shoulder makes contact and rotating tool is held in a place for about 3 to 5 seconds, for example, depending on the type and thickness of the material. This pause allows enough heat to build up through friction at the tool metal interface. That heat causes metal to plasticize, making it soft and ready to flow, which ensures smooth movement of the tool in the next stages. After that, we have the welding stage. Now, the tool moves forward along the joint line while continuously rotating. During this time, friction and deformation keep generating heat, and the material around the pin gets stirred and mixed. The plasticized material flows from the advancing side to the rear of the pin, and the shoulder forges the softened material at the back, which effectively closing the gap created by the tool movement. There are three important functions during friction stir additive manufacturing to generate frictional heat, to control material flow, and to keep the plasticized material beneath the shoulder. It's worth noting that in thin sheets, most of the heat comes from the shoulder, while in thicker plates, the pin plays a bigger role. Also, specifically designed shoulders and pins can improve both heat generation and material flow. This entire stirring process leads to dynamic recrystallization, which produces fine aqueous grains and results in excellent mechanical properties in the weld joint. Finally, the retracting stage. Once the weld reaches the end of the joint, the tool is lifted out This leaves a small exit hole, but in practice, welders often extend the weld length slightly or use refilling techniques to avoid this hole. In friction stir additive manufacturing method, next we are going to see the friction assisted seam welding or FASW. This technique was patented in 2014, and the schematic, you can see the schematic diagram in the figure 9. The process is fairly straightforward. Two plates or sheets are placed one over another. Then the pinless rotating tool is pressed down axially onto the top of the surface of the upper plate. Because of the rubbing action between tool and the plate surface, frictional heat is generated, which makes the top surface plastically deformed. As the axial force continues, this deformation progresses through the thickness until it reaches the top surface of the bottom plate. The rise in localized temperature here is due to the both heat transfer from the tool and the continuous stick slip action, which enhances plastic deformation. Now, by repeating this step, similar to the way we do in friction surfacing, we can also perform multi-track seam welding. Coming to additive manufacturing using FASW, here we join multiple layers, either in a single track or a multi-track manner. Although studies are limited, this method has been successfully used for materials like aluminum 6061, titanium Ti6Al4B, and stainless steel 304 in both a similar and dissimilar combination for thicknesses ranging from 0.5 mm to 5 mm. The results are quite promising. FASW plates have shown higher tensile strength compared to the parent material in most of the studies. These improvements comes mainly from two factors. The formation of the first one is the formation of strong metallurgical bonds between the overlapping layers, and the second one is the development of fine recrystallized grains at the weld zone. For example, the microstructure of in one study, the microstructure of FSW welded 304 revealed grains extending from one plate to another due to diffusion at the interface. This diffusion, along with recrystallization and stick slip effects, is what ensures good metallurgical bonding. Finally, when the tool is allowed to move forward along with given path, we achieve continuous seam weld. Next, moving on to the additive friction stir processes or AFS. Unlike most of the techniques we discussed earlier, which involve both additive and subtractive step, AFS is a purely additive process. That means the component is built directly by depositing material on a substrate layer by layer. One of the biggest advantages of AFS compared to other friction stir additive techniques is that it can use a wide variety of raw materials, something like tubes, metallic sheets, and even powders. In fusion-based processes, powders usually melt and then solidify, which often leads to defects like porosity and solidification cracks. But in AFS, the powders are only softened and plastically deformed, not melted. This prevents those solidification-related defects and produces refined ecoexit grains, giving the final part enhanced mechanical properties. Now let's look at the working principle. Here, the filler metal, usually in the form of consolidated powders, is applied through the center of the hollow rotating tool. As the axial pressure is applied, frictional heat is generated, which softens the powder and causes plastic deformation. With the right combination of heat and pressure, a strong bond is created between the substrate and the filler metals. So the process allows multiple tracks to be deposited layer by layer. As the tool is raised to match the required layer thickness, the filler metal keeps getting forced onto the previous layer. This results in diffuse bonding across layers and ultimately produces the pot with homogeneous microstructural properties. The outcome is quite impressive. The material undergoes grain refinement and the pot shows improvement in ductility and toughness. However, the one challenge is that this process can sometimes introduce anisotropy, meaning the properties may vary depending on the direction, build direction. So To get the best results, careful optimization of process parameter is essential. So some of the key parameters that needed to be controlled in AFS. First one is tool rotation speed and traverse speed, and plunge depth and tilt angle, and geometry of the hollow tool shoulder, and deposition rate and layer thickness. And the final point is spacing between successive layers. Since the material is deposited directly without needing much post-processing, AFS can fabricate parts that are near net shape, which is a huge benefit in terms of time and cost. The next one is friction stir additive manufacturing. It is a well-known technique in both the welding and additive manufacturing world. This is relatively novel technique that combines the principle of additive manufacturing and friction stir welding. The first patent on friction stir additive manufacturing actually came out in 2002 and later. Later, companies like Boeing explored its feasibility for fabricating aircraft parts. Since then, FSIM has gained a lot of attention in research because it allows us to fabricate materials layer by layer with exceptional structural performance compared to the base materials. So, well, FSIM not only fabricates a component but also gives us the ability to control and modify microstructure of the part. That means the microstructure can actually be tailored to meet specific customer requirements. As a result, the parts produced by FSIM generally show improved mechanical properties. In fact, even high-strength metallic alloys have been successfully fabricated using these techniques. Now let's look at the working principle. The schematic of friction stir additive manufacturing is shown in figure 12. Similar to friction stir welding, it uses a rotating non-consumable tool that is inserted into a set of overlapping sheets or plates. These sheets are often then friction stir lap welded in a particular direction to build up the part. The heat for joining comes from the two things. The first one is friction between tool and the plates, and second one is the plastic deformation of the material. Interestingly, studies have shown that 54% of the heat comes from the friction, while the rest is from the deformation. This heat combined with material flow around the tool causes the plates to consolidate at the back of the tool, forming a solid joint. The final thickness of the part depends on various factors, something like the thickness of each sheet, how the sheets are arranged, and the total number of sheets, the dimensions of tool pin, and plunge depth of the tool. Also, the tool position during welding directly affects both the microstructural features and overall geometry of the part. Some of the key parameters that need to be controlled in FSAM are tool rotation speed, traverse speed, plunge depth, and tilt angle. Different researchers have optimized these parameters for different materials. Now let's move on to the steps in FSAM. First, the sheets are placed or machined to the required dimensions and flatness, and then they are cleaned. Next, two plates are stacked one over another as per the required orientation. Once arranged, the process parameter are set and the friction stir lap welding is carried out. If the desired height of the part is reached, the process can stop there. But if not, the welded surface is machined again to remove any flash and to flatten the surface. Then another sheet is added on the top, and the whole process is repeated until the required height is achieved. This layer by layer approach not only build bulk part but also allows to create functionally graded materials, that is FGM. These are really interesting because they have a gradual variation in properties across their volume, making them ideal for advanced engineering applications. Let's break down what happens to the microstructure during friction-based additive manufacturing. Things like friction state additive manufacturing. Unlike fusion-based additive manufacturing, where melting and solidification cause a lot of complicated changes, this process works entirely in the solid state. So the metal gets heated by friction, state mechanically, and shaped without ever melting. Just give me a minute. When we look into the microstructure of fusion-based additive manufacturing, fusion-based additive manufacturing such as laser powder bed fusion or direct energy deposition involves layer by layer melting and solidification of metallic powders to build parts. The microstructure evolution during fusion additive manufacturing is primarily driven by rapid localized melting, followed by very fast solidification rate, often millions of Kelvin per second, and steep thermal gradients. This rapid solidification creates distinct microstructure dramatically different from those in traditional casting and forging. One hallmark feature of future is directional solidification, where the metal solidifies with strong anisotropy due to steep temperature gradient, driving epitaxial grain growth from the substrate or prior layers along the build direction. The resulting grains are typically elongated, columnar, and aligned with thermal gradient, often forming cellular and dendritic structure. This famously leads to a strongly textured microstructure with 0, 1, 0, 0, 1 and 1, 1, 0 crystallographic orientation, commonly observed in FCC metals such as stainless steel or nickel-based superalloys, which strongly influences mechanical behaviors. During directional solidification, competitive grain growth occurs, whereby grains oriented favorably to the heat flow, resulting in a robust texture along the build height. This columnar microstructure reduces grain boundary area perpendicular to the load, but can lead to anisotropic mechanical responses such as high strength and lower ductility along build direction due to fewer transverse grain boundary to impede slip. Fusion-based additive manufacturing includes fusion-based additive manufacturing includes technology like selective laser melting, electron beam melting, and wire arc additive manufacturing with distinct microstructural features due to differences in heat source, heat input, and cooling rates. Selective laser melting uses high-power laser to selectively melt layers with rapid localized heating and cooling cycles. The microstructure in SLM parts typically exhibits very fine cellular and dendritic structure, as we see in figure 13. With the dendritic structure with a strong directional solidification along build direction. Because cooling rates are extremely high, microstructure shows very fine and primary dendritic arms spacing and fine subgrain cellular structures. For example, in nickel-based superalloys like Inconel 625, SLM produces fine columnar or epitaxial grain growth aligned to the build direction with a strong crystallographic texture. The rapid solidification also produces supersaturated solid solution and fine precipitates, enhancing strength, but sometimes resulting in residual stresses and anisotropic mechanical behavior. Scan patterns, laser parameters influence grain orientation and size with different scan strategies, yielding varied microstructural features and mechanical anisotropy. Electron beam melting EBM follows similar powder bed melting approach, but uses a focused electron beam and operates under vacuum with relatively high preheating temperatures. This preheating reduces residual stresses and distortion compared to SLM. The microstructure of EBM parts often contains coarser grains than SLM due to slower cooling rates, but directional solidification leading to columnar-like grains is still dominant. The higher build temperature promote in situ aging and phase transformation during the build, altering precipitate size and distribution. Grain morphology can be tailored by changing scan strategies, and the overall texture tends to be strong along the build direction. Parts often exhibit relatively isotropic mechanical properties when scan strategies encourage equiaxial grain formation. Although columnar grain structures remain common where line scanning melting is used. When it comes to wire arc additive manufacturing, it deviates more from powder bed methods by using an arc welding heat source and feeding wire to deposit material. Wire arc additive manufacturing typically produces larger melt pools in slower cooling rates and consequently coarser microstructure. The typical microstructure consists of large, highly oriented columnar grains aligned with heat flow direction. For example, in 316 cell stainless steel VAM pots, gamma arsenic matrix with dendritic ferrite phase is common, with lamellar perlite and grain boundary ferrite structures seen in steels. Cooling rates are lower than in SLM or EBM, so defects like grain coarsening and thermal gradients are more pronounced. Mechanical properties such as toughness and strength depend strongly on grain size and morphology. With post processing, uh, post processing often required to refine microstructure or relieve stresses. Beyond microstructure, the fusion additive manufacturing process also leads to defects such as porosity from unmelted powder or trapped gases. Residual stresses cause rapid thermal cycling and micro cracks, all of which degrade mechanical performance, particularly fatigue life. Surface roughness from partially melted particles adds another fatigue stress concentrator. However, careful process parameter optimization and post-processing treatments like hot isostatic pressing (HIP) can mitigate many of these fusion-based issues. The mechanical properties of fusion-based additive manufacturing parts are just highly microstructure dependent. Strength and hardness are generally enhanced by the fine non-equilibrium microstructures and monolithic or cellular features, but it may trade off ductility and toughness. Overall, fusion-based additive manufacturing creates complex microstructure shaped by rapid solidification and directional grain growth that impart a unique blend of high-strength, moderate ductility, and anisotropic behavior. Microstructural evolution in friction-based additive manufacturing is overwhelmingly governed by the dynamic recrystallization (DRX). A direct consequence of this intense plastic shear and frictional heating imposes by rotating tool. During the friction surfacing process, the material in the process zone is subjected to very large strain at elevated temperature, well below the melting point. Those conditions produce a very high dislocation density and promote recovery and rearrangement of dislocation into subgrain structure. In high stacking fault energy metals such as aluminum and nickel, this is typically proceeds as continuous dynamic recrystallization, that is CDRX. Subgrains forms and gradually rotate and absorb dislocation until low angle grain boundaries converted into high angle grain boundaries, which producing new and stain free equiaxial grains. This behavior is exactly what the EBSD images reveals here in figure 14 and 15. The substrate, which is base material, retain its original coarser grain structure with fewer newly formed high angle grain boundaries because it has experienced little or no severe plastic deformation. By contrast, the deposited that is processed region shows a dense population of much finer, large equiaxial grains and an increased fraction of high angle grain boundaries. The hallmark of dynamic recrystallization. Intermediate zones, that is thermomechanically affected zone, and which is TMAZ, often show elongated or heavily deformed grains with many low angle boundaries, reflecting partial subgrain formation and a progressive boundary rotation towards full recrystallization nearer the still or deposition region. The microstructure development produced by dynamic recrystallization has direct consequence for properties. The finer recrystallization grain size increases strength by Hall patch effect. It can improve toughness and fatigue resistance, and tends to randomize or weaken the strong rolling textures of the substrate. The final grain size and boundary character, however, depending on processing variables, that is tool rotation speed, traverse speed and heat input and number of passes, and alloy features, solute content, precipitate, particle population. Excessive heat or prolonged thermal exposure after dynamic recrystallization can cause grain growth and partially erase the refinement. So process control is essential to retain the fine recrystallized microstructure, as we seen in the EBSD maps. In the case of alloy salmon, right, the EBSD image of a friction surface deposit clearly highlights a very fine equiaxial structure with a large fraction of high angle grain boundaries. This significant refinement is a direct result of dynamic recrystallization, which occurs under the combination action of severe plastic deformation and frictional heating during deposition process. Recrystallization in general can occur in two distinct ways. One is static recrystallization, which takes place during annealing after deformation, and dynamic recrystallization, which happens simultaneously with hard deformation. Since friction surfacing subjects the material to very high strain and elevated temperature conditions, the recrystallization observed here is best explained by the dynamic recrystallization. The specific type of DRX mechanism, dynamic recrystallization mechanism, operating is strongly influenced by the stacking fault energy of the material. For example, aluminum alloys, as I said earlier, which have a relative high stacking fault energy, typically undergo continuous dynamic recrystallization. In that process, the dislocation rearrange into subgrains, and with progressive strain, these subgrains gradually rotate and transfer into new strain-free grains. The UVST misorientation maps provide direct evidence for this mechanism. And the maps, the blue lines represent high angle grain boundaries, which is greater than 15-degree angle. Green line represents low angle grain boundaries, that is 5 to 15-degree angle, and red lines represents subgrain boundaries, that is 2 to 5-degree angle. In the deposit, the majority of the boundaries are clearly high angle, while low angle and subgrain boundaries are appear only in small fraction. This dominance of high angle grain boundaries, along with the scarcity of subgrains, aligns perfectly with the discontinuous dynamic recrystallization mechanism expected for alloy 718. The limited presence of subgrains is mainly because the low stacking for energy hinders dislocation recovery and subgrain rotation, making continuous dynamic recrystallization almost negligible. This microstructural refinement is not just of academic interest, but has important implication for properties. A fine grain structure with a high fraction of high angle grain boundaries, which enhances strength through the Hall patch effect, which improves the toughness by disrupting crack propagation and provides better resistance to fatigue. However, it is also important to note that while fine grains are beneficial at room temperature and moderate temperatures, for very high temperature applications such as those faced by nickel-based superalloys, extremely fine grains can sometimes promote grain boundary sliding and reduces creep resistance. Therefore, balance between grain size and high angle grain boundary fraction must be carefully considered depending on the internet service condition. In summary, while aluminum deposits formed by friction-based additive manufacturing primarily refined by continuous dynamic recrystallization (CDRX) due to their high stacking fault energy, whereas alloy solenoid behaves differently with microstructural evaluation dominated by DDRS, that is discontinuous dynamic recrystallization. The EBST evidence of fine grains and predominantly high angle boundaries confirm this, and it reflects the characteristics response of low stacking fault energy alloy under the severe thermomechanical conditions imposed during friction surfacing. In solid state additive manufacturing, heat input plays a crucial role in determining the final microstructure and material properties of a deposited layer. Unlike fusion-based process where the material is completely melted and resolidified, solid-state process rely on severe plastic deformation and frictional heating to achieve bonding. As I said earlier, the temperature generated during friction surfacing generally ranges between 0.2 to 0.8 times of melting temperature of material. The exact fraction depends on the alloy system under consideration. If you take alloy solenoid as an example, the thermal analysis during friction surfacing clearly shows how the temperature rises in a highly localized manner, restricted mainly to the immediate contact region at the consumable electrode tip and the substrate surface. This localized thermal profile offers significant advantages. The advantages are uh, the advantages of low and localized heat input are it minimizes the distortion and residual stresses since only a narrow zone is heated without affecting the bulk of the substrate. It prevents large heat affected zones and thereby maintains the integrity of the base material. It reduces the oxidation and thermal degradation as the material is not held at elevated temperature for long periods. It limits the grain corrosion in the deposited layer, preserving the refined microstructure achieved by dynamic crystallization. And also, it allows better property retention, making the deposited surface layer suitable for high performance applications. When we look at the cross-sectional image of a consumable electrode in figure 16, which is used in friction surfacing, we can see that the heat generation indeed occurs primarily at the tip of the electrode, where direct metal-to-metal contact and shear action takes place. The generated heat then dissipates simultaneously into the substrate and into the electrode rod, preventing excessive buildup in any single region. Another important point can be derived from the temperature versus time plots. During friction surfacing of alloy solenoid, the thermal profile shows that the deposited sample begins to cool rapidly once the frictional contact is stopped. For instance, within about 30 seconds, the temperature drops down to nearly 250 degrees Celsius from 1100 to 250 degrees Celsius. This rapid cooling has various microstructural advantages. Since the deposition temperature never reaches the full melting point, the material undergoes dynamic crystallization, producing fine nacreous grains at the surface. Due to the rapid cooling, these specially formed grains do not have sufficient time to grow further. As a result, the fine decrystallized microstructure is retained, and with it, the desirable mechanical properties such as high strength, fatigue resistance, and improved wear resistance. This behavior clearly demonstrates why solid-state additive manufacturing processes like friction surfacing are highly effective for alloys such as Inconel 78625 and other high-temperature superalloys, where maintaining microstructural stability and mechanical performance at high temperatures is critical. Solid-state additive manufacturing generally produces uniform microstructure because the process involves intense plastic deformation, localized heat below the melting temperatures, promoting dynamic recrystallization through the deposited layer. This mechanism refines grains and achieves metallurgical bonding between layers without the coarse microstructure typical of fusion processes. The consistent localized heat input and deformation cause fine aqueous grain to form uniformly across the layers as deformation paths and recrystallization conditions remain similar within each deposition cycle. However, some cases exhibit microstructural difference between layers, typically in grain sizes or morphology, due to the complex interplay of heat dissipation, and then reheating and thermal gradients during successive layer deposition. The primary reasons are heat generated at the deposition zone zone is rapidly transferred to the substrate and a previously deposited layer. The underlying layers experience varying degrees of thermal exposure depending on the spatial location relative to the heat source. So heat flows downward through cooler the substrate material and upward through newly deposited material, which leading to different cooling rates and temperature profiles layer to layer. And second one is the reheating effect. Higher layers are subjected to partial reheating by subsequent deposition passes. This reheating can increase local temperature of lower layers just enough to cause some grain growth or additional dynamic recrystallization, which alters the microstructure compared to freshly deposited top layer. The extent of reheating is influenced by process parameters and interlayer time delays. Then third one is thermal gradient and cooling rates. Variation in local cooling rates causes difference in grain size. Faster cooling rates promotes finer grain size, while slower cooling due to substrate preheating, thick deposited material or heat accumulation result in coarser grains in some layers. Thermal gradients influence dendritic morphology and phase precipitation as well. And the final one is mechanical deformation differences. The deformation path through the thickness of deposited layer is not uniform. Edge regions may experience pure shear, while central regions undergo more complex deformation. This leads to subtle heterogeneities in grain size and boundary character between layers or across the build thickness. However, these microstructural difference between layers typically do not translate into significant variation in mechanical properties, unlike fusion-based additive manufacturing. The key reason is that solid-state additive manufacturing process avoid melting and resolidification, which are primarily responsible for common defects and heterogeneity in fusion AM, such as porosity, hot cracking, and segregation. In fusion-based additive manufacturing, the melting and solidification cycle causes pronounced microstructural coarsening, uneven grain growth, and the formation of unwanted phases or depressions, which can create weak interfaces or anisotropic mechanical properties between layers. In contrast, whereas in solid-state processes produce continuous metallurgical bonding through plastic deformation and dynamic recrystallization, which maintains consistent mechanical strength across and between layers despite minor grain size variation. Furthermore, the rapid cooling and limited heat affected zones help to retain fine grain structures and reduce residual stresses, thereby preserving mechanical integrity throughout the build. This controlled solid-state thermal cycle ensures that differences in grain size between layers caused by heat dissipation or reheating do not impact properties such as tensile and fatigue resistant or hardness, resulting in components with uniform and reliable mechanical performance. In some cases, researchers found there are a lot of banded structures in their deposited material in both friction surfacing additive manufacturing and friction stir welding additive manufacturing. The banded structures in the microstructures of solid-state additive manufactured components primarily forms due to periodic variation in local processing conditions that affect microstructure evaluation during solidification or deformation stages. In processes like laser powder bed fusion, LPPF, this band arises from oscillatory instability of the solid-liquid interface during rapid solidification. This leads to alternating regions of different solutes segregation levels and morphological features, such as an alternation between featureless solute supersaturated zones and pattern regions with the secondary phases precipitates. These banded structures are aligned roughly normal to the main temperature gradient and solidification direction, reflecting the dynamic solidification condition like changes in cooling rate and melt pool behavior. In solid-state additive manufacturing methods such as friction stir or linear friction additive processes, the banded microstructures can form due to periodic thermal and mechanical inputs variation during layer-wise deposition and bonding. Factors like tool speed, downforce, feed rate, and localized heat cycles, which influence grain size, grain shape, and texture oscillation, causing band of different microstructure characteristics along the build direction or across the layers. Overall, band structures form because of periodic oscillation in local thermal gradients and cooling rates during rapid solidification or layer bonding. Alternate Alternating solution modes and solute segregation developing due to this translation. And for last reason is mechanical and thermal cycling during additive process that leads to microstructure heterogeneity and grain growth variation. Such bandits microstructure are commonly observed in both fusion and solid state additive manufacturing. In fusion process, these bands often have a strong influence on the mechanical properties because they are associated with variations in solidification structure, segregation, and residual stresses. However, in solid state additive manufacturing, the effect of banding on properties is much less pronounced. This is because the overall microstructure is dominated by fine recrystallized grains produced by severe plastic deformation and dynamic recrystallization, which largely govern the mechanical response and tend to homogenize the performance despite the presence of banding structure. When it comes to defect formation and elimination of defects in solid state additive manufacturing, especially in friction stir welding, friction stir additive manufacturing can broadly be categorized into volumetric defects and surface or joint line defects. Understanding these defects and how they correlate to process parameters allows avoiding them and achieving sound joints. When it comes to volumetric defects include unbounded regions or voids inside the deposited or joined material volume. These voids are unbounded. These voids or unbounded regions degrade mechanical performance and require machining to remove. In solid state additive manufacturing, by friction-based methods, improper material flow or insufficient bonding energy causes these defects. Other defects in FSW-based solid-state additive manufacturing arise mainly due to incorrect parameter settings such as tool rotation speed, welding, traverse speed, tool tilt, plunge depth, and force. There are various surface defects or subsurface defects are falling in place in terms of in the friction-state additive manufacturing. The first one is surface galling, which is caused by excessive sticking of material to the tool pin, often due to too high weld pitch or excessively hot weld, creating protrusions and lumps on the welded surface. And second one is excessive flash, excess material expelled from the joint area caused by excessive heat input or improper tooling force, leading to material overflow beyond the joint line. Then the weld nugget becoming collapsed or deformed due to improper heat input or low material flow. Then the tunnel defects, cavities or long voids within the weld caused by insufficient heat input and plasticization, leading to material not fully flowing or filling the weld zone. These defects may appear below the surface or as surface tunnels. Then the lack of penetration, joint incomplete fusion along the thickness due to insufficient welding energy or improper tool placement. And kissing bond, barely bonded interface often caused by outside layers or insufficient stirring, where surfaces are in contact but metallurgically bonding is weak. It occurs if the tool stirring does not access key interface regions. And finally, one is wormholes, a type of tunnel defect with a narrow elongated void in the stir zone, which is often parameter dependent. The parameter and process control to avoid effects are rotational speed and traverse speed. The first one is rotational speed and traverse speed. Determine heat generation and material plasticization. Too low or too high values lead to cold welds, such as tunnels, lack of penetration, and overheated defects, such as flash and galling. Tool tilt and plunge depth, which affect the tool material contact and material flow. Incorrect setting cause incomplete bonding or surface roughness. And welding force and pressure, which ensures frictional heat and proper forging. Insufficient force causes irregular thickness, unwanted zones. Then tool design, pin length, shape, shoulder size, impact, materials steering, and heat distribution, which influencing the defect formation. So by carefully optimizing these parameters through process control, monitoring, and experience, most defects can be missed or avoided. Techniques such as real-time parameters adjustment, in-situ monitoring, or machine learning prediction may also be employed to maintain a defect-free process. So when we see the application case studies of solid-state additive manufacturing, several industries have adopted solid-state additive manufacturing techniques such as friction state additive deposition and cold spray for repair and joining application due to their advantages of solid state bonding, minimal thermal disruption, and superior mechanical properties. Key industries include aerospace industry, where widely used for repairing, joining, and reinforcement of aerospace structures like wings, fuselage, engine components, and turbine blades. Solid-state additive manufacturing prevents heat-affected zones issues which is common in fusion welding, enabling repairs of high-value, life-critical parts without degrading material temper or inducing cracking. Examples include repairing corrosion or wear damage on aircraft parts, and manufacturing lightweight stiffness and structural components. And the second one is automotive industry. Solid-state additive manufacturing applied to manufacture, join, and repair automotive body structures, components like seat frames, and critical parts with complex geometries, which enable joining of dissimilar metals and composites used in modern lightweight vehicles, improving fuel efficiency and performance. Repairs of worn and damaged parts can be done more cost effectively with solid-state methods. And the third one is oil and gas industry, where solid-state additive manufacturing used for repairing pipeline cracks, wear on drilling equipment, and joining metallic components exposed to harsh condition. Solid-state repair reduces downtime and extends asset life while maintaining material integrity under high pressure and corrosive environments. Then infrastructure and heavy equipment. Solid-state additive manufacturing used for repairing high-value components that experience heavy load and wear, thermal fatigue, and erosion and corrosion, which enables restoration of geometry and mechanical properties with minimal material waste and energy consumption. In railway and shipbuilding industry, solid-state additive manufacturing utilized for fabricating and repairing metal parts and structural components subjected to cyclic loads and harsh environments, which allows production of large-scale components are repaired without large heat inputs, which reducing distortion and residual stresses. In medical industry, medical implants and biocompatible porous metals for tissue integration via solid-state additive manufacturing, porous structures, small structures with embedded sensors via ultrasonic additive manufacturing for aerospace, automotive, and consumer products. These adoptions examples demonstrated solid-state additive manufacturing's versatility in joining and repairing, where thermal effects from fusion welding are detrimental. The processes offer superior metallurgical bonding, control microstructure, and cost-effective localized repair solution in critical application across high-value industries. I have summarized the challenges and future trends of solid-state additive manufacturing. When it comes to challenges of solid-state additive manufacturing, first one is material limitation, which is primarily effective for ductile material. Challenges exist with high-strength, brittle, or reactive alloys. Anisotropy, second one is anisotropy in mechanical properties. Variations in bonding between layers can cause anisotropy in strength and ductility. When we see the process control complexity, precise control of parameters, that is tool speed, force, feed rate, those are critical to avoid defects and achieve consistent quality. Then microstructure control, where we face the difficulties in uniformly tailoring grain size and phases. Center-based method may cause grain growth. When it comes to scale and speed, we faced the challenges in producing large parts efficiently with record speed and surface finish. And also solid-state additive manufacturing requires post-processing There is a requirement for post-processing like machining or heat treatment to improve properties. And limited data on automation, less established than fusion-based additive manufacturing. So solid-state additive manufacturing is less established than fusion-based additive manufacturing with fewer process automation tools and standardized monitoring. When it comes to future trends in solid-state additive manufacturing, expanded material. First one is expanded material change research to include more alloys, composite and multi-material deposition, and advanced process monitoring and integration of sensor technologies and machine learning for real-time defect detection and parameter optimization is needed. Then hybrid manufacturing, combining solid-state additive manufacturing with fusion or subtractive method to capitalize on complementary advantages. Then porous and functionally graded materials. Fabrication of complex microstructure for medical implants, lightweight aerospace parts, and thermal management. Energy efficiency and sustainability. Further reduction in energy demands waste during manufacture. Then automation and scale up developments in robotics and automated tool changes for higher throughput and complex part fabrication. Then final one is tailored microstructure and properties. Ahead lies better control of recrystallization, grain formation, and phase distribution for superior mechanical and functional performance. So one big challenge in solid-state additive manufacturing has always been continuous material feeding, basically having to keep feeding material in smoothly so the machine can keep building without any interruption. So that's where MELD manufacturing really shines. MELD has MELD is nothing but the company, manufacturing company. It has designed a cool machine that automatically feeds a solid metal rod continuously while building the part. The best part is it's all controlled by computer, so the whole process is super precise and consistent. This combo of continuous feeding and computer control means you can create really complex and freeform shapes that other machine might struggle with. MELD process never melts the material because it's a solid state additive manufacturing. Instead, it uses friction and pressure to soften and deposit the material from the rod onto the base material. MELD is changing how industry like aerospace, automotive, and defense think about fabrication and repair. We can repair worn and broken parts, add new features onto the existing pieces, or make entire big complex metal parts, all with excellent quality. I can also show you a short video of a MELD machine in action to see how smoothly it works. I'll play the video. Here, if you see, the spindle moves along different direction, which is controlled by computer program, and the consumable material is fed continuously through the spindle. So this seamless operation will eliminate the defects during start and stop of the process, and this will eliminate the defects which are produced during layer to layer transition during deposition. So we can build a number of layers seamlessly to get large size complex commercial products. I hope this gives you a clear picture of how MELD technology tackles one of the biggest hurdles in solid state additive manufacturing and open up exciting new possibilities for metal 3D printing. So up to this, I will wrap up the seminar for today. I will continue the sustainability in solid state additive manufacturing on Thursday. Thank you for listening. Any questions? If you have any question, you can ask.
My sincere thanks to Dr. Cyril Joseph Dani. Thank you, sir, for providing a detailed core concept of friction-based solid-state welding, additive manufacturing, and its microstructural characterization. Now the session is open to audience to clarify your doubts. Please. Any clarifications from participant side?
If you don't have any question to ask now, you can contact me through my email. Professor, you can share my personal email ID to participant.
Yes, sir.
I can also answer through email.
Sir, can you see the chat box?
Okay.
Some queries are coming through the chat box.
Okay. Wait, I will check.
So what are the improvements in additive manufacturing for the last 5 years? This is the first question. Recent improvements in additive manufacturing.
Okay. They're asking what are the improvements in additive manufacturing
Very recent improvements. They're asking about the recent.
Okay. There are various factors researchers have improved in additive manufacturing. The first one is better material selection, wide range of materials, and they're built using solid state additive manufacturing, such as metals, superalloys, lightweight materials, dissimilar materials, even polymers and composites. And second one is higher precision surface finish, which improved accuracy and reduced defects. Then the third point is faster production, advanced machine, like as I said, MLD technology, which can provide higher build rates within the quick time, which can improve the efficiency in the industry, and also larger build volumes, ability to print bigger parts. For example, in IIT Madras, there is a research center called Agnikul Aerospace Industry. They built a full engine part by using VAM technology, wire arc additive manufacturing, which are a bigger milestone in additive manufacturing. And multi-material and functional integration, combining different materials in one build. In various researchers working on functionally graded materials, and also the building scanning strategies, deposition methods, material selection, all those things improve mechanical properties, which gives stronger and denser and more reliable parts. And also overall it reduces cost, production cost in the industry. So these are the key improvements in additive manufacturing in the last 5 years.
Thank you, sir.
Okay.
Is there any difference between solid state welding and additive manufacturing? They are asking about the clear difference between solid state welding and additive manufacturing.
Solid state welding and additive manufacturing.
Yes.
Okay. Solid state welding is nothing but the welding processes. We can only join one or two materials put together. But additive manufacturing, we can add a number of layers and build thick parts. That is the two difference between solid state welding and additive manufacturing. Joins two existing workpiece is welding, solid state welding. Additive manufacturing build a parts layer by layer without with or without melting. So we can build parts with record dimensions. So that is the difference.
So next question is regarding to customized polymer composite filaments. Polymer composite filaments. Where to get the polymer composite filaments, sir?
Actually, many industries provide polymer filaments like PVC, other polymer filaments. As I said, the MELD industry also making uh, machines for polymer-based additive manufacturing. So we can get polymer filaments from third-party suppliers, and we can utilize the technology like MELD. We can produce multiple layers of polymer coating.
Practical applications of AIM from Javed Salim.
Sorry, sir, I can hear you.
Practical applications of AIM.
Of AI in additive manufacturing, huh?
No, no. Generally, he asked about practical applications for of AIM.
Oh, it's a general question. Okay.
General question. Yesterday, we have discussed a lot of applications regarding to
Mm,
AIM.
Nowadays, AI is used by many industries. In our manufacturing industry, we can use it for design optimization. AI-driven generative design creates lightweight and high-strength structures. And we can utilize the AI for process monitoring and control, real-time defect detection using sensors, cameras, and machine learning models. And we can use it for quality prediction. AI predicts porosity, cracks, or distortion before printing finishes. No, companies like ESAB, Lincoln, all those building companies are utilizing AI for identifying online defect in during welding. So we can use it for quality prediction. Then we can use it for process parameter optimization. Automatically, AI will automatically select best laser power, speed, layer thickness, and predictive maintenance. In additive manufacturing, we can use it is for to predicting the maintenance and material development, which accelerates discovery of new alloys, polymers, and composite, which will give you a better combination of materials, material composition, especially in functionally graded materials. So we can use it AI for different purposes in manufacturing industry. So yes.
Next, regarding to high strength alloys.
Okay.
How to process high strength alloys in solid state additive manufacturing.
Oh,
High
using
strength alloys.
additive solid state. Okay.
Yes. The process is the solid state AIM process.
Okay. Mm, yeah, it is possible to fabricate high strength alloys using solid state additive manufacturing. And in fact, solid state additive manufacturing often better uh, properties than fusion based additive manufacturing for such alloy. Because there is no melting, which can avoid hot cracking, porosity, and segregation, which are common in high strength alloys like titanium, nickel, and aluminum based alloys. And fine eco-extreme microstructure, frictional, which will give frictional heat and severe plastic deformation, refine the microstructure. So anyhow, it will solid state additive manufacturing gives you a fine microstructure, so that it will improve the mechanical properties. So that we can get a higher superior mechanical properties than the existing fusion based additive manufacturing methods. So we can use friction state additive manufacturing and friction state deposition and cold spray additive manufacturing techniques. We can utilize all those techniques for high strength alloys. So yeah, we can able to build parts using solid state additive manufacturing.
This will be the final clarification. Why the solid state additive manufacturing depends more on plastic deformation and diffusion rather than melting.
Sorry, can you repeat one more time?
Why solid state additive manufacturing depends more on plastic deformation and diffusion rather than melting.
Okay. Mm,
So in melting, there is no, I think
Actually,
melting, there is no plastic deformation.
okay. Actually, plastic deformation is the one of the key thing in solid state additive manufacturing. So, uh, because in fusion based additive manufacturing, there is no uh, pressure or force or strain uh, acted on the fusion based additive manufacturing. So there is only temperature will act in fusion based additive manufacturing. But in our case, solid state additive manufacturing, it will depending on heat plus severe strain will act on the material. So we are going to apply high pressure uh, as well as the temperature. So with the combination of temperature and the pressure will create the plastic deformation. That's why the solid state additive manufacturing more depending on the plastic deformation. So the reason is pressure and the temperature. Uh, in fusion welding, there is no pressure, right? So that is the reason.
In what way it is useful in aerospace applications? So yesterday
Okay.
also we have discussed aerospace application by it is clarified with by
Okay.
Dr. A.K. Lakshmanarayanan sir.
Okay.
So now the
In,
same question was asked by Vignesh Kumar, aerospace application regarding to aerospace applications, sir.
okay. In aerospace application, solid state additive manufacturing used to build a turbine blades, shafts, and other high temperature applications components like the discs 720 disk 7018 and it requires dissimilar joints. It also used to repair the worn out parts. By using, we cannot do the repairs on high temperature parts by using existing fusion based additive manufacturing, but we can repair the damage or worn out parts using friction based additive manufacturing. So because the friction based additive manufacturing provides a localized heat input which won't affect the whole part. In fusion, if you are doing repairs by means of fusion welding, it involves high temperature, so it will affect the whole part. So in friction based, whereas in friction based additive manufacturing, we are working on well below the melting temperature, so the lower temperature will not affect the whole part. So we can do the repairs or deposition or coating anywhere anytime without affecting the base material. That is one of the major important thing, advantages of friction with solid state additive manufacturing in aerospace industry. So because the aerospace components are very crucial, right? Uh, if you give a high temperature to the material, it will change the property immediately. So the main thing is lower heat input. That's how the solid state additive manufacturing works in aerospace application.
Thank you, sir.
Okay.
So
Any
now,
questions?
yes, no more questions, sir.
I'm not able to see the questions. Okay, okay. No more
So it
question.
is all questions are in chat box.
Okay,
I'm
okay.
reading from the chat. Yes, sir.
Okay,
We can conclude session 2, session 3. Next, we will
okay.
move on to session 4. I request Dr. Yermani, sir, to take over the session.
Okay. May I leave the conversation?
Yes, yes, sir. Yes, sir.
Okay. We will see on Thursday on
Thank you.
sustainability in additive manufacturing. Thank you. Thank you, sir.
Thank
Thank
you.
you.
I request Dr. B. Yermani, sir, to start session 4. Sir, Dr. Yermani, sir.
Sir, 1 second. Am I audible, sir?
Yes. Yes, sir. Yes, sir.
Okay.
Sir, you can start session 4, sir.
I'm starting, sir. I'm starting
Yes,
the
sir.
presentation.
Thank you.
The presentation is visible, right? Hello.
Yes, sir. Visible.
Hello.
Visible, sir. Visible.
Okay, okay. Okay, sir. Fine. So, very good evening, one and all. Welcome to this session on material jetting and binder jetting, principal practices and applications. So, these two are the material jetting, shortly MJ, and binder jetting are fascinating branches of additive manufacturing technology with their own advantage, limitations, and industrial relevance. So, we'll discuss the fundamentals of both the processes and their working principles, different materials that can be printed using MJ as well as BJ process. And we'll analyze the various applications of the two processes. So we'll begin with material jetting. So material jetting, as defined by ASTM, is the process of creating objects by selectively depositing tiny droplets of material, which are then solidified by layer to build a three-dimensional part. This is very much similar to inkjet printing that we generally use, but except that in a material jetting that is printed in a three-dimensional, one print over another print that is being printed. In material jetting, uh, like uh, like SLS and FDM, we use filaments, we use powders, but in material jetting we use inks, right, or liquid materials. That is the distinct feature of these material jetting process. So the material jetting is, widely regarded as a cost-effective and high-throughput technology, especially when the precision surface finish and multi-material printing is the need. And the applications are already cover, a broad spectrum of applications. You can have a microsystems with embedded electronics, optical lenses, functionally graded materials, bio-inspired structures, microfluidic systems, kind of different applications through the material jetting. The material jetting process is very simple. No, you have to print through jet, you have to cure it, right, and it generally uses a support structure. Then you can remove the support structure and use the product. But there are challenges in the material jetting. The challenges are in a different perspective. You have a very limited inks. That means you have a very limited materials that can be printed in material jetting. And there is certain thing called waveform optimization in a droplet formation that we'll discuss later. And the interaction between the material jetted from the nozzle and the interaction between the substrate, which is already printed, and the curing is post processing, and the multi-material compatibility and the characterization of the inks also poses certain challenges for the material jetting process. And there are distinct limitations of the material jetting process. The low mechanical and thermal properties of the material jetted inks, they lag in mechanical as well as thermal performance compared with the other additive manufacturing technologies possess the limitation of the process. But there are three or four different categories of the material jetting process that we will discuss one after another. So These simple pictorial representation depicts the working principle of the material jetting. The working principle is very straightforward. We have a print head similar to that of a 2D inkjet printer. It deposits droplets of the built material onto the substrate or a built platform, and these droplets are cured immediately, usually using UV light. And the system also uses support materials alongside the build material. So you have a multiple nozzles, and some nozzles used to print the material, uh, build material. Some nozzles used to print the support materials. And there are these are all the major parts of any multi-jet printer. It includes precision printers, a controlled built platform which moves upward or downward based on the layer thickness, and a system to control the droplet, and integrated UV curing units. The advanced multi-jet printers have a multiple number of nozzles to enable different colors or different materials in the same product. For example, you have a polyjet from Strategies. They can produce multiple materials with excellent resolutions. And you also have a XJets nanoparticle jetting that allows you to use metals that we'll discuss. So there are three distinct uh, type of material jetting machines available. We have a polyjet, we have a multi-jet from 3D systems, and we also have a XJet or nanojet, right? So these three multi-jet printers are commercially available printers uses three different principles. The Strategies polyjet uses continuous printing. That means it continuously ejects the ink on the substrate along with the support. Whereas the multi-jet printing of 3D systems uses drop-on-demand system. Wherever required, the nozzle deposits the ink, and further, these two systems uses for curing UV light, and these two systems can only print polymers. And we have another MJ multi-jet system from XJet's nanoparticle jetting, in which the ink contains nanoparticles of metals or ceramics. So you can have a metallic pot or ceramic pot. Here, instead of UV light for curing, we are using heater, because this ink is very much different from that inks used in polyjet or multijet. In polyjet and multijet, they use photopolymers as ink. Here, we use nano binders with nanoparticles, and these inks contains nanoparticles of metals and ceramics, whatever you require. After the ink gets printed layer by layer, we'll have a, heating source. That heat source will cure the component. So, what I'm trying to say is we have a two different kind of multi-jets. One type of multi-jet uses either continuous ink, continuous drops, or drop-on-demand setup, but uses photopolymers as the build material. Whereas the nanoparticle jetting uses a different type of ink which filled with metallic or ceramics nanoparticles. One type of multi-jet printers uses UV light to cure. These nanoparticle jetting uses heater to harden the component. The performance of the material jetting process is closely relevant to the type of inks that can be jetted or ejected through the nozzle. So various types of inks are available. They include phase change inks. They solidify on cooling. Water-based and solvent-based inks. The solvent will evaporate and leave the green part behind. Or you have a UV curable link or a hybrid combinations of these particular different types of links. But the UV curable inks are dominant because they are solvent free. and they are fast curing. They are suitable for 100% solid thing. However, they have a certain drawbacks. You have to have a photo initiator inside the monomeric liquid, whereas the monomers sometimes become toxic. And these, UV curable liquids are not biocompatible, so it limits the applications in pharmaceutical or food industries. And the recent research is going on in the functional inks. Functional ink means the ink has certain properties. Whether the ink can be an electromagnetic ink, so you can print an electromagnetic. Is any queries? Okay, 1 second. I'll mute. Okay. So there is a research on functional links. So beyond basic polymers, material jetting is moving towards functional links, that enable electronic, magnetic, and structural functionalities. For example, you can have a ink with oxide nanoparticles for electromagnetic application, inks with metallic nanoparticles, ink with ceramic nanoparticles, different pigments. So these are all called functional links. They are developed with high performance printers that can handle high viscous ink. And there are certain limitations for the inks. The print heads can print inks of a certain property. These properties, different properties of liquid, you have to study. Not all inks are suitable for inkjetting. The feasibility is usually evaluated using some dimensionless numbers. We know Reynolds number, we know Weber number. So the ratio between Reynolds and Weber, we have a OH number. So for ink to be printed, the that OH number should be between 1 to 10, and the viscoelastic nature, the non-Newtonian nature also need to be studied. Then only the ink can be determined whether it can be printable or not. So this is the present scenario of the available inks with the Z value 1 to 10. That is optimum viscosity. In future, the research is moving towards the high viscous printing, where the printed is capable of printing high viscous non-Newtonian fluids as a ink. And in multi-jet printer, in material jet printer, there are two types of inkjet or ink drop generation are generally used. One is a continuous stream of droplets, that is CIJ, continuous inkjet, and another is drop on demands. In a drop on demands, droplets are ejected only when needed using thermal or piezoelectric mechanisms. So this is a schematic representation of continuous inkjet printing. You have a ink feeding mechanism and with an actuator. So the actuator continuously drives the feeder and continuously develop ink drops. And we have a drop catcher at the bottom, a drop catcher, drop watcher also you can call it. So the drop catcher determines whether the particular droplet touches the surface of the substrate or not. So the droplet catcher is controlled by your STL file toolpath. It catches the droplets wherever that material need not to be printed. It allows the droplet touch the surface wherever it needs to be touched. So here it is continuous inkjet printing. The droplets are forming continuously, but the droplet catcher determines whether to print, whether to not to print. On the other hand, so this is used in uh, polyjet, and this is used in DOD is used in multijet. So the DOD is drop on demand. So we have an actuator which receives the pulse train signal This pulse train signal is determined by your STL file. So the pulse train signal is given to the actuator and determines when to generate a droplet. So the actuator, usually there are two different types of uh, actuators are generally used. One is thermal based droplet generator, and another one is piezo based droplet generators. In the thermal based droplet generators, the constraint given to the heater, where the heater develops pressures inside the ink jet or ink nozzle. So based on the pulse strain, the heating takes place. So the droplet formation is thermally controlled, whereas in piezo ceramic controlled droplet formation mechanism, the pulse strain given to the piezo ceramic, based on the pulse strain, the piezo material will vibrate. uh, so the pulse strain determines whether the piezo to vibrate or not. So the vibration controls the drop formation. So I'll repeat. There are two different mode of inkjet printing. One is continuous inkjet printing, where inkjet is continuously developed. In drop on demand, inkjet is developed, or the drops are generated whenever required. Here it is controlled by droplet catcher, and here it is controlled by the pulse train. The pulse train is controlled by your STL file and toolpath generated by your software. And in drops generation, usually in a DOD type of drop generation, the waveform, that pulse train waveform is important parameter which determines the droplet size, droplet frequency, all those things. And you have to optimize the droplet frequency so that it doesn't affect the printing process. And there are certain issues in a drop generation that needs to be uh, optimized or avoided. The air bubble entrainment, usually a major issue in droplet generation, as well as impurities. Sometimes they form nucleation, they trigger nucleation. That means two or more droplets assemble together to form a larger drop. So then So the another important thing in multi-jet printing is the droplet and the substrate interaction. When the droplet hit the substrate, the substrate means the base surface. At the first layer, the substrate will be the built platform. Usually, glass or PET or metal built platform will be there. So, how the ink drop interact with the substrate after the previous printed layer, the previous printed layer will act as the substrate. So how the ink reacts when it interact with the substrate. So that has to be optimized. And so after you generate drops from the either continuous drop or drop on demand, the drop touches the substrate and forms a layer. Then it has to be cured. So we have two different types of curing mechanisms in polymer based material jetting. We have a free radical kind of reaction, we have a cationic reaction. These two are photopolymeric reactions. In free radical reaction, the photon, that is UV, interacts with the photoinitiator, and the photoinitiator will eject a free radical, which which converts the liquid monomer into a solid polymer. Whereas cationic, again the same thing. We have a photoinitiator of cationic nature, and the photoinitiator receives UV energy and it ejects a cation. That cation initiates the polymerization process. But the free radical polymerization is generally used in acrylate systems. They usually of rapid curing, but they have a problem of oxygen inhibition. That means the oxygen surrounding the polymer will slow down the polymerization reaction or slow down the solidification. In a cationic polymerization that is usually used in epoxides, they have don't have these oxygen inhibition issue, but they are very sensitive to humidity and they are very slow in curing process. But there are hybrid photopolymers available. They mix free radical as well as cationic photopolymers to optimize both the problems of oxygen inhibition and humidity and slower curing rates. So choosing the right amount of free radical, choosing the right amount of cationic reaction, choosing the right amount of photoinitiators uh, decides your mechanical stability of your product as well as the surface quality. So for UV curing, there are two different UV sources are used. One is mercury arc based UV source. Uh, the traditional mercury lamps, they have a broad spectrum of UV wavelengths. We know that the mercury arcs are toxic in nature and highly energy intensive. And we also have a LED based UVs. But LED based UVs are, even though they are compact, they are efficient, they are safer, but they provide a narrow spectral range of UV. But the photopolymer may require a broad spectrum of UV. So nowadays the hybrid systems are used. You have a mercury arc based UV for providing high amount of UV, as well as you have a LED based UV system for uh, optimized curing process. And if we so we have a different curing strategies also. uh, we have a cure after level, that is immediate curing after deposition. The first thing is you have deposited one layer, then you eject UV rays, cure the particular layer. But the issue is once the layer is cured, the next layer deposited over the cured layer will cause the delamination issue. The interconnection between these two layers may not be good as solid materials. So the another strategy used is called a pinning, whereas the deposited layer will not be cured entirely. They partially cured with a 5 to 10 percentage or 1 to 5 percentage of UV energy to convert the liquid into gel-like state. So the spreading will be controlled, and the next layer will be printed over it, and that also pinned. So finally, after printing all those layers, finally they completely cured using a UV ray.
போஸ்ட் கம்ப்ளீஷன் இருக்கு போதுமா?
So these pictorially represent the effect of pinning, where the pinning determines the spreading of layer. When less amount of energy used for pinning, the layer thickness will be high, that won't spread. If the pinning energy is high, they will spread over the surface. Almost all the polyjet and multijet UV based material jetting process require post curing. That means they have to cure the inside thermal ovens or UV chambers. Sometimes even electron beams are also used for post curing. So these post curing enhances the cross linking and between the polymers, and it improves the mechanical strength. But excessive curing can also sometimes causes brittleness, sometimes discoloration or warping also may take place. When you use multi-material builds, in the same product, if you use multiple materials and different curing requirements for different materials, so it will create an additional challenge. So the optimum post curing strategy for heterogeneous parts is always a hectic task. And the multi jet printers have some quality issues. There are a number of issues like any additive manufacturing uh, process, but these are all some of the major issues because it is uh, from liquid monomer to solid or liquid nanoliquid to solid. Shrinkage takes place. So shrinkage, we all know the volume reduces. So the uneven shrinkage sometimes causes failure of the components, warping. So we have to optimize the curing strategy, optimize the ink combination so that shrinkage is minimal, right? Sometimes in general we have to use support material also. So if the support material and the build material have different shrinkage properties, that will also causes quality issues. And the other is important issue is the layer rate variation. So the consistency in a layer rate, which determines the smoothness and accuracy of the final part. We know that the problem arises when there are nozzle inconsistencies. Sometimes some nozzles may fail. Sometimes some nozzles may eject a larger size of a droplet. Uh, some droplets will be smaller. So the droplet errors causes uneven layer thickness. Sometimes the support will also have a, unsmooth surface. So some systems, no, they use rollers to level after each layer is printed, but the roller sometimes may remove excess the photo liquid, sometimes break the minute features also. And the oxygen inhibition, as we already discussed, is also an issue. When you use UV curable resins, the oxygen in the environment can slow down the, sometimes even prevent the polymerization of the UV curable resin. So usually the oxygen inhibition issue is a two-edged sword. Sometimes it is positive in the sense the oxygen inhibition reduces the polymerization process of the layer. So the next layer will have a better bonding. But the top layer, if you're having oxygen inhibition, the outer surface will be tacky. So you have to optimize the oxygen inhibition. That's why we are going for hybrid inks. So beyond shrinkage as well as the oxygen effects, there are issues like gas dissolvement, where the bubbles uh, trapped with gas. So it leaves pores inside the printed product. Or we have a well-known coffee ring effect, where the particles in a single droplet migrate to the droplet edges during the evaporation process. So it causes uneven deposits. And so these figures summarizes some of the issues in multi-jet material jetting process. So if you have a nozzle failure, you have a droplet volume variation, you have a position error, that means the droplets deposit in a different position, or the droplet shrinkage after the solidification. Sometimes the substrate also have uneven surface. These are all various defect scenarios which causes issues in the final product. So material jetting, applications we'll discuss now. So they become very popular in healthcare, due to its precision and ability to use biocompatible materials. Uh, we'll see anatomical models, that allow the surgeons to plan complex procedures, or medical education, dental prosthetics, orthodontic devices can also be printed with the material jetting. And the aerospace and automotive sectors, uh, material jetting is primarily used for prototyping and rapid tooling applications. They can rapidly produce full color multi-material models, to evaluate fit and design before moving to the final production or final call. For tooling applications, material jetting provides precise molds and patterns to reduce lead time, in compared to conventional machining process. Although the structural applications of the polyjet or multijet type of material jetting uh, are limited, we have structural applications of the XJet and nanoparticle application. So, as we discussed, there are two variants. One variant uses photocurable polymer. They generally used for these kind of multicolor printing, aesthetic applications, or mold making, indirect tooling making. Whereas these X-jet nanoparticle jetting, that is one type of material jetting process, they can able to produce ceramic as well as metallic components. For example, hydraulic systems, sensors, and high precision surgical tips, uh, wearable, you know, accessories. Those things can be printed using these nanojetting by XJet. And these potential applications, as I say, in electronics industry, the material jetting with the evolution of functional links. The functional link still in the developmental stage or research stage. So the functional links uh, in material jetting can effectively print conductive tracks, dielectric layers, or insulating supports on PCBs, various electronic components like RFID antennas, wearable electronics, microfluidic devices with integrated sensors. These are all possible applications with the functional links. With a sustainability perspective, in terms of energy use, material jetting is relatively efficient when you compare with the laser-based processes like powder bed fusion. Uh, it mainly consumes less amount of energy for curing. However, the photopolymer resins are difficult to recycle. So these, uh, has a potential hazardous environmental concerns. So these recycling of UV based photopolymers needs high amount of research. And there are certain advantages of material jetting. So the advantages are very clear. No, it offers very smooth surface finish, highest detail and accuracy, multi-color, multi-material in a single product. And post processing is, still there is a post processing, but it is minimal when compared with other powder based products processes. Still, the limitations are also very important to understand. So you can play with the you can improve the process. So the uh, multi-jet and polyjet uses photopolymers. They are expensive and they offer very limited mechanical performance. They cannot be used for structural applications. And the printers are sometimes slow. Large printers are sometimes slow. Always they require support structure. The support structure, so you have two types of nozzles. One nozzle prints build material, one nozzle prints support structure. So these are all some of the disadvantages of the material jetting process. So the future of the material jetting depends on certain parameters and overcoming these material as well as process limitations. You have to develop evacuable inks with better mechanical as well as thermal properties, and the development on the printers for printing high viscous particle filled fluids for improved material capabilities. And you have to optimize the waveform for stable droplet generation. These are all potential for the further research, further improvement of the material jetting process. And you have to improve the curing methodology. You have to improve the material availability. All those things are uh, need to be developed. So, in conclusion, I'll say material jetting is for high precise multi-material uh, challenging products can be printed. So here UV inks are used, but they are very limited functional applications. In case of nanojet, ceramics as well as metals can be printed. So the material jetting has a wide range of applications starting from electronics, bio, pharmaceutical industries, medical industries. Next, we'll move on to the binder jetting process. So binder jetting, you can it is, yesterday we discussed about powder bed fusion process, right? It is very similar to powder bed fusion process. In powder bed fusion, you have a powder which is fused together using a thermal energy, usually laser or electron beam. Here in binder jetting, we also have a powder bed. The powder is spread on the bed. They are bound together by a binder. That is the only difference between a powder bed fusion and a binder jetting process. So the binder jetting is, another powder-based additive manufacturing technology. It was developed in MIT in the 90s. Uh, you know, it doesn't use any laser or electron beam or UV light, and it usually operates at room temperature. It uses a liquid binder, nothing but a glue, right? The binder deposits selectively over the spread powder, so it creates a green part. Uh, the ASTM defines the binder jetting process, an additive manufacturing process in which a liquid bonding agent is selectively deposited to bond powder materials. And in practice, it means instead of melting or sintering like powder bed fusion, we bind powder granules with liquid adhesive. Uh, Only a fraction of volume the binder gets deposited. The remaining powder may act as a support structure. So it requires less energy when comparison with the other all additive manufacturing process. But here the catch is the post processing steps in binder jetting is very energy intensive. So that we'll discuss. So this figure depicts binder jetting process. Again, the working principle is relatively very simple, and you can compare it with SLS, or you can also compare it with the material jetting. Uh, I'll compare with the SLS. In SLS, we have a powder bed, and we spread the powder to the required layer thickness. On top of it, we'll have a laser source. That laser source selectively sinters the powder, so you will have a solid part from the powder. Here, same process. You have a powder bed. You spread the powder to the required thickness, and you have a liquid binder which is jetted similar to the material jetting. So the inkjet formation, all those droplets formation, all those mechanisms that we have discussed in a previous process, material jetting, is also applicable here. We also use either a continuous uh, binder jet or drop on demand binder jet here. So there are two types of jet generation or drop generation that are very comparable with the material jetting principle. So a thin layer of powder is spread across the build platform, and the printed nothing but a nozzle which deposits the binder droplets onto the required areas, which is controlled by STL5. So these binder creates adhesion between the particles in those regions. So this process, again, the next layer is deposited, and the printed deposits binder. So this process repeats until the entire part is printed. After printing, the object is removed from the surrounding loose powder. The usually binder won't be cured. Sometimes UV or heat source is used to cure the binder, but even though UV curing is used in some commercial machines, it definitely has to undergo severe rigorous post processing, I will say, because it is as printed binder jetting product is very fragile. It is still in green state, very weak in mechanical structure, very porous, right? So you have to convert the green part into structurally rigid part. You have to convert the porous part into dense part. All those things are done in a post-processing state. So here, usual schematic uh, post-processing arrangements are here. So after the first few steps, A, B, C are a printing process. You start with the D in post-processing. So after C, you do de-powder. That means the unbound powder has to be removed. Then it has to be put inside the curing oven. After cleaning the part, there are two subparts. One is infiltration. That infiltration is usually for densifying the porous product, or other way you have to burn out the binder. We use binder, right, to print the product. So you have to remove the glue from the part, then you have to put into sintering, either infiltration after sintering or burning out binder after sintering. So uh, so you'll print using a powder binder together, and the material is fed to the build platform either manually or automated feeding of the material. Then printing process is controlled by your CAD profile. Then printing process starts with the deposition of the binder. Then curing. It is usually an optional step. Either sometimes you'll have a UV curing setup with the machine itself, where the binder is partially cured. After that, we'll have a post processing that we have discussed. No, post processing usually involves infiltration, thermal treatment or heat treatment, hot isostatic pressing, as we discussed in SLS, to improve the density, grinding and polishing to remove the unbound powders on the surfaces. So a binder jetting usually consists of the power supply and recoating system that printed will be there at the top, and we'll have a build platform with for the powder deposition, and we'll have a heating system to assist the curing of the binder. As like material jetting, here also we use piezoelectric or thermal inkjet printers at the top to precisely place the binder droplets. The recoating speed, the powder flowability during each layer, and the binder viscosity all impact the product quality and reliability. And compared to the powder bed fusion that we've discussed yesterday, this binder jetting is less complex, but the precise synchronization between all those powder spreading, binder deposition, uh, the leveling platform, all those are very crucial for the accurate part printing. So in material jetting, unlike the sorry, in binder jetting, we will use all the engineering materials like polymers. You can have a ceramics, you can have a metals, you can also have a composites. So for metals, we can go with stainless steel, inconel, titanium alloys, various whatever metal powders you have, you can use it in material jetting. Using binder jetting. Whatever ceramics, whatever polymers, whatever composites, all those are possible in binder jetting because it is determined by the binder, and the final product needs to be go through a huge amount of post processing steps. And binders are generally produced based on the powders that used. We have organic binders such as polymers, waxes, and we also have inorganic binders like silicates. They're usually suited for ceramics, and specialty binders are being developed for reactive materials and other special purpose applications. So the interaction between the binder and the powder are very essential for the uh, strength, porosity, defect formation in the product. So the controlling of the binder and the powder interaction needs to be studied, needs to be optimized. Now, when the powder droplets, it touches the binder droplet touches the powder bed, they interact in very complex ways. We can see whether the binder on a powder bed, they can penetrate more or they can spread more. So it depends upon the binder nature and the powder nature. Powder nature in the sense powder size, powder type, whether it is a metallic, ceramic, or polymer, what kind of binder we are using, what is the viscosity of the binder. All those things determines how much it penetrates, how much it spreads. So the penetration as well as spreading has to be studied well so that the required amount of binder is deposited through the nozzle. So these are all the possible three mechanisms that when the binder interacts with the powder. One is tunneling. So tunneling means the binder rolls over the surface and forms a bigger chunk of powder balls. Whereas in spreading, the powder is not usually disturbed. The binder gets attached to the surface and spreads to the required area. And sometimes crater formation also takes place when the binder hits the powder surface and the powder surface gets a crater. So the crater formation and the tunneling needs to be avoided. So we need to have a proper spreading of the binder over the surface. And the proper spreading and the proper penetration is also determined by the thickness of the powder you spread. The powder layer also determines the uh, how binder is spread, how depth your binder is spread. So you need to be very optimum thickness. If the thickness is very small, no excessive spreading will take place. If the thickness is very high, the binder won't penetrate to the required depth. So you have to play between the layer thickness as well as the binder quantity to get the required amount of penetration, required amount of spreading. Also, the powder ejection is also one of the major issue in binder jetting printers. When the you can see in the clear video, when the binder hits the surface of the powder particles gets ejected from the surface. Though they are very small in quantity, they affect the property of the product. So you have to study all those tunneling effect, powder ejection, crater formation, so that we reduce defects in the final product. So, binder jetting performance usually depends upon these particular process parameters like binder saturation, how much amount of binder you're going to use, what is the layer thickness you're going to use. Generally, it ranges from 50 to 200 micrometer. What is the droplet size you're going to use? The droplet size also matters. If the droplet is very minimal, very small in size, it won't penetrate enough, it won't spread enough. The droplet is very large chunk of droplet, it may create a crater, it may eject the powder from the build platform. And we also have a print resolution, recoating speed, all those parameters also very vital to ensure the quality and the mechanical property of the build product. So as we discussed earlier, the binder jetting products needs a very high amount of post processing. So the post processing starts with depowdering, where the unbound powder is removed from the green part, uh, and then it puts inside the oven for removing the uh, solvents in the binder. Then sintering takes place. Sintering usually for densifying metal as well as ceramic parts. Sometimes infiltration also required. Like suppose if you want to increase the density of the product, because the binder jet products are usually porous in nature. After sintering, they have a very porous texture. So you can infiltrate, if it is a metallic product, you can infiltrate it with metallic liquids. So the liquid metal or bronze kind of metal liquids are generally used for infiltration. They infiltrate the pore structure and improve the density and improve the surface finish. And the surface finishing operation also one of the post processing. So you have to use different surface finishing like polishing, coating, sometimes machining. These are all to remove the unbound powder, also to machine a few micron of the surface to get the required finish. Now we will discuss the advantages and the various applications of material jetter. So this binder jetting process, you have a different advantages. It eliminates the thermal stress in the printing process. Like in a powder-based process like SLS or SLM, there are huge amount of thermal stresses on the built product. But here, again, we use powder. We can build ceramic or metallic parts, but with less thermal stress. And you can have a large build volumes in binder jetting, so you can have a large scale production, and its productivity is very high. You can have a different types of materials. That means it has a very high material versatility. uh, and additionally, the binder jetting can print full color. So color means it can handle, the ink, the binder ink can be of a different color, so you can have a multicolor products. And now we'll discuss various applications of these binder jetting. So we have a different metallic binder jetting process with different applications like lightweight brackets for aerospace, automotive components, rapid tooling inserts, right? All those metallic components. And the figure at the left side, you can see there are two blades. One is the green component. The right side one is the final product. That black color one is directly from the printer. After post processing, after curing, after infiltration, we'll get the metal part out of the metal part for your application. You can also have a You can also have heat exchangers with complex internal channels. You can have a lightweight structural components, and low volume in production induced products also can be printed using the binder jetting. In sand mold, binder jetting is very standout application in molding. In binder jetting, you can print metal, you can print ceramics, you can print polymers. You can also print the green sand, which is usually used in molding casting applications. So in foundries, binder jetting is in foundries, the binder jetting is used to fabricate large and large scale components, large scale molds for casting, large scale cores for casting, and very complex core structures, very complex patterns that also printed using sand as the build material. So this will reduce lead time in foundries when you need to produce very complex products in casting. And in ceramics, we have a different kind of applications. You can print zirconia, you can print SiC, you can print various type of ceramics. So these zirconia oxide ceramics are used in biomedical scaffolds with porous structure. There are certain very distinct advantages of the binder jetting process over other additive manufacturing technologies. It generally require no support structure, as the unbound surrounding powder provides a natural support, and it is compatible with wide range of materials. It can print metal, it can print ceramics, it can print sand, it can print polymers, you can name it, it can print it. Only thing is it needs to be in a powder form, and you can print a very large scale with less energy consumption during printing, and multi-material and full color printers you can get from the binder jetting. But the limitations also are equally significant. So the parts from the binder jet machine is very weak in nature, very porous in state, and they require very extensive post processing. The porosity control is a major issue in binder jetting. Infiltration is possible, but you have to use liquid metals, sometimes bronze, that cannot be compatible with the required metal. So infiltration also can be done. HIP, that is hydro, as we discussed, isostatic pressing also can be used to increase the density. Still, porosity is a major issue in the binder jetting process. And as we discussed in material jetting, in binder jetting also, there are very unique quality issues are there. One of the major issue in binder jetting is feeding of the powder on the build platform. Either you can underfeed or overfeed. That is going to be issue. And the powder migration, powder binder bleeding is going to be issue. The binder is deposited on a particular place. When the binder is can migrate inside the layer, and it can bleed outside the product also. That is one issue. And powder segregation means the tunneling effect will cause the powder segregate in a certain places. And incomplete curing, that binder may not cure in all places in a uniform manner. That is also one of the issue. And you can have a smearing effect, you can have a smearing and cracking, and the delamination between the interlayers because of the issues with the binders. The different layers won't stick together. These are all some of the potential issues in the binder jetting. Now, the recent trends are towards improving the mechanical properties and reliability of the binder jetting products. The nano binders, nano additives in the binders may increase in future the green part strength. And there are hybrid approaches with combining binder jetting with hot isostatic pressing. That after binder jetting, we it's followed by a HIP process that yield dense metal parts. And functional binders are also being researched for application like self-healing or conductive components. As in any field, AI-driven parameter optimization, AI-driven control, machine learning-based control is also in a research trend. As we've discussed, the sustainability aspect of the binder jet also need to be studied. So, binder jetting has a very high powder reuse because the binder is spread in a very limited recovered area. So the remaining unbound powder can be reused multiple times. So it reduces waste, and energy consumption is very less because you just build it on a room temperature and you use just a binder. But there are issues, the binder toxicity and the emissions from the binding process, emissions from the further curing process. All those things needs to be studied in the environmental perspective. So in conclusion, I'll say binder jetting has various advantages of the material jetting as the first process we have studied. Compared to material jetting, binder jet has some additional advantages. Uh, it is faster than the material jetting. So binder jetting is faster than the material jetting. And second, the combination of powders are available for the binder jetting is high compared to the material jetting. So in material jetting, the powder is very limited. The uh, material is very limited, whereas in binder jetting you can have different types of material. And thirdly, high range. You can build very large parts, ceramic or metal parts can be produced. And binder jetting is also the same advantage of material jetting. You can print multiple colors, multiple functional parts you can print. And in comparison with the material jetting and binder jetting, we'll say there is they may look similar, but there is a slight difference in the mechanism of the process. In material jetting, it is droplet deposition and followed by curing, either UV curing or heat-based hardening. In binder jetting, we use binder or glue. Then followed by rigorous post processing. In material jetting, we can use photopolymers and nanoparticle inks for metal and ceramics. Where in binder jetting, we directly use metal powder, we use ceramic powder, we use sand as the product. And the resolution is very high in material jetting, whereas in binder jetting, comparatively, it's a moderate resolution. And post processing, material jetting is simple support removal. Usually, uh, soluble supports are used in material jetting. They are either water soluble or alcohol soluble, so it's easy for support removal. So post processing is very limited post processing required in material jetting, whereas in binder jetting, you have to debind the unbound powder, you have to sinter, you have to infiltrate, you have to heap. All those post processing is very rigorous in binder jetting. And in sustainability perspective, uh, material jetting is have a limited recyclability. That means we cannot recycle the photopolymers, whereas in binder jetting, we can reuse the powder, less energy consumption. So in comparison with the material jetting, binder jetting is highly sustainable in the environmental perspective. But both material jetting as well as binder jetting, very costly materials, costly uh, print, costly machines. Both lack of standards and the scalability issues. You cannot mass produce using both the machines. They have a specific advantages. They can be adapted for a very particular applications. They have issues with their mechanical strength. They have issues with the uh, aging related issues. For example, in material jetting, the photopolymers cannot be used with a humid environment or with a high temperature environment. So they can lose the mechanical property as soon as they hit a particular threshold. So with this with this, I'll end my presentation. If there are any queries, you're feel free to ask.
A sincere thanks to Dr. Erumalai sir for providing core concept of binder jetting and material jetting with detailed applications. Now the session is open to participants to clarify your doubts. Please. Our expert is ready to clarify your doubts.
Okay, either I assume that there are no doubts.
Sir, can you see the chat box, sir?
There is no message after 8 p.m.
Are there any sources available where we can get information about the compatibility of different binders with the materials?
Okay, I'm getting any message. Can you read it again, sir?
Information about the compatibility of different binders with the materials. Compatibility with binders and materials.
Uh, you know, these binder jetting and material jetting, there are very specific machines available. Uh, we have discussed the strategy 3D systems as well as XJet. They have a very commercial machines like FDM or like SLS. You cannot play with the process parameters. You cannot play with the materials. Like if you have a HP printer, you need to have a HP what do you call cartridge you have to buy, right? Similar way, if you have a material jetting or if you have a binder jetting machine, you have to buy the ink from the manufacturer only. That material that ink only compatible with that printer. That is the major drawback in the material jetting as well as binder jetting. Like FDM, in FDM you can develop your own filament. You can adjust the nozzle temperature, bed temperature. You can print it. But in case of MJ as well as BJ, this cartridge, that ink or binder has to be obtained from the uh, machine manufacturers. Like if you have a HP printer, you have to get the cartridge refilled with the authorized HP dealer. Similar way.
Any other
Hope
clarifications? One question from Abhishek.
Okay.
What kind of water works soluble support structures used in binder jet and material jet? How can we recycle the support structures?
Uh, 1 second. Well, there are two different types of support structure are used. One is water soluble, and other one is luminous soluble. As we call. So the it got stuck. I'll just tell the exact name. 1 second. Okay. The exact names now. I had the document here. Okay. I'm not able to get the exact name now, but there are two types of soluble support structure. One is water soluble, where the support structure dissolves in water. So you just print with the water support soluble support structure. Then you don't have to break the supports like if you do in a FDM. You just immerse that product inside the water. The soluble support structure dissolves into the water. Also, we have a luminous soluble support structure where it doesn't dissolve inside the water, but it dissolves inside the citrus-based solvents. So we generally have two different kind of soluble support structures. I don't remember the exact names of the structure, but there are two different types of soluble support structures are available.
So why the photopolymers commonly used in material jetting?
No, can you comment again? Photopolymers.
Why the photopolymers are commonly used in material jetting?
Okay. Not photopolymers. The basic principle of the material jetting process is like that. The material is jetted from the nozzle in a liquid state. After it is deposited over the build platform, it is cured. So there are two ways of curing it. One is you have a liquid which is photopolymer, which is that means it is liquid in initial state. When a photon hits the polymer, it is converted into solid. That is one type of curing process that is used in polyjet and multijet by 3D system as well as status. That is one kind of commercial machines. In another kind of commercial machines, you have a nano jet technology. In nanojet technology, we don't go with photopolymers. You have a nano particles inside a liquid, a binder usually. That liquid contains a high amount of nanoparticles, usually metals and ceramics. Once the nano link deposited, you have a heat source which removes the binder and leaves the metal or ceramic parts together. So there are photopolymeric based systems and there are non-photopolymeric based systems. The photopolymeric based system is for polymers production, where the non-photopolymer based systems for metals as well as ceramic production. Not always material jetting means photopolymer, but the initial development starts from the photopolymeric UV curing material jetting. But at present, there are two commercial systems. So one uses multi-jet, that is a continuous printing, or polyjet that uses drop on demand. Both works on the UV curing principle. Whereas the nanojet from the XJet industry that uses hardening principle, in which you have a heat source which hardens the nano liquid.
So next one is the UV curing essential in polymer material jetting, sir?
Yes, yes, definitely. Yes.
Does the curing
UV
speed
curing
affect
is
the
the
layer addition?
curing. No, as we have discussed now, there are two different types of photocurable polymers: cationic polymers and uh, free radical polymers. So the free radical polymers has one particular property, cationic polymers has one particular property. The cationic polymers are very slow in nature. The curing process is very slow in cationic polymers, but the free radical polymers cure in a faster rate. But the oxygen inhibition is the problem. But the cationic polymers are free from the oxygen inhibition problem, but they are brittle in nature. So you have to mix them in a way that you have to get the advantage of both the cationic reaction as well as free radical reaction. That means you have to optimize the quantity of free radical reaction, quantity of the cationic reaction. On the other hand, you have something called photo initiators. That photo initiator only initiates the liquid to polymer reaction. That the photo initiator is like a it is also a liquid or some kind of molecule. It receives the photon from the UV rays. It ejects either free radical or a cation. So the amount of photo initiator inside your liquid decides the curing rate. And you also have a stabilizers. So the stabilizers will limit the curing, control the curing rate. So all those needs to be optimum. If you cure it very fast, warping takes place, it becomes brittle. If you cure it very slowly, the parts become tacky and they will sag. No, so you have to optimize the cooling rate. Usually, the curing strategies we have discussed, right? There are two curing strategies: immediate curing as well as spinning. So immediate curing means once you deposit a particular layer, immediately you will cure, then you will deposit next layer. But these causes delamination issue, because once the layer is cured, next layer cannot bind together. So most of the systems uses pinning. Pinning means a fraction amount of UV rays only used, so partially solidify the liquid deposited, so that next layer has required binding between previous layer. Once all the layers are printed, they will cured inside a UV container or UV oven. Yes, the curing rate needs to be optimum.
Thank you, sir. Any other clarifications? Yes, sir. No more questions, sir. We can wind up the session 4.
Thanks for patient audience. Thanks for the opportunities.
Once again, I thank you, sir.
Thank you.
Yes, thank you. Thank you.